Welcome to Future Talk. On today's program, we're going to talk about string theory. It's a theory about the most basic units of matter and energy, and it could potentially change our entire understanding of the physical universe. In string theory, all matter is composed of tiny vibrating strings that exist in 10 dimensions at once, and it appears to explain certain forces, such as gravity, better than more conventional theories. My guest is Leonard Susskind. He's the Felix Bloch Professor of Physics at Stanford University and Director of the Stanford Institute for Theoretical Physics. Professor Susskind is considered one of the fathers of string theory. He was the first to introduce the idea of the string theory landscape and was the author of the 2005 book, The Cosmic Landscape, which was one of the first attempts to bring string theory to a general audience. Leonard, welcome to the program.
Thank you, Martin. Glad to be here.
So tell me, what exactly is string theory?
Well, it's what you said. It's a theory of the most fundamental particles and the most fundamental forces in nature. Everything is made out of particles. You're made out of particles. I'm made out of particles. And those particles interact with each other, exert forces on each other. Electromagnetic forces, magnets, electric charges, gravitational forces. And string theory is a theory of all of this. It's simultaneously a theory of matter, that means the particles which make up matter, and the forces that hold them together.
Now, why are they called strings? I have an image of a string as something you tie a package with. Is there a similarity?
Yeah, there is. For whatever reason, string theory is a theory of particles in which the particles are little one-dimensional threads of energy. They vibrate. They do everything that an elastic string, a rubber band, might do. They can spin, they can stretch, they can vibrate, and they are the particles of nature, at least according to this theory.
Now, quantum theory also attempts to explain the action of matter and energy at the smallest scale. How is string theory different from quantum theory?
String theory is not different from quantum theory. Quantum theory can describe many, many things. It can describe atoms, it can describe the nucleus, it can describe photons. It's a way of thinking about objects. String theory is just one of those objects which is susceptible to being thought about in quantum mechanics. So string theory is a quantum mechanical theory. It's a theory which makes use of quantum mechanics. It's not different than quantum mechanics. It's, if you like, a special case of quantum mechanics.
Now, what are the characteristics of a string? What can a string do?
Well, it can vibrate, just like think of a rubber band. Think of a little rubber band. There are actually two kinds of strings that string theory deals with. They're closely related. Start with a rubber band. Take your scissor and cut it. You have what is called an open string, a string with two ends. You, of course, can stretch it. You're not there at those tiny, tiny microscopic levels to be able to pull and push on one of these fundamental strings, but they can hit each other, they can vibrate, they can spin around an axis. They can do all the things that you would imagine that this cut rubber band can do. And then there are closed strings. Closed strings are just like the rubber band before you cut it. Both those things are present in string theory, and they both play a role. For example, the open strings, in many examples of string theory, the open strings which have ends can represent photons. You know what a photon is? A photon is a light particle of light. Not a light particle in the sense that it's not heavy, but a particle that makes up light. In the same way that there are particles that make up light, there are particles that make up gravity. Those are called gravitons. Gravitons in string theory are represented by these closed strings. Now, people didn't just make this up. This was not just a whim. You know, I think I'll make up a theory in which photons are open strings and gravitons are closed strings.
Well, does string theory explain something that quantum theory doesn't?
Yes, it explains why there's gravity. Quantum theory by itself has no explanation of gravity. It's not inconsistent with gravity, but it doesn't produce gravity out of it. Gravity is something you would put in on top. String theory is a theory which makes use of gravity, but which automatically, it can't help itself but have gravity. So it explains gravity in that sense. That's what makes it unique and different than other theories like atomic theory or nuclear theory. String theory itself explains why there is gravity. That's the special thing about it.
Now, how can we visualize that without getting into long equations?
Yeah.
I mean, how do we explain that one object exerts a pull on another object that's a distance away from it? Is it there are particles going back and forth?
Yes, exactly. There are particles going back and forth. I don't know if I can do this with my hands properly, but imagine a string here. From one end to another end, there's a string. And now the string joins and splits. It joins and splits, and this piece of it could go over to another string, be exchanged with another string. That transfer of a closed string between some other strings is what accounts for gravity. So gravity is the exchange, or you said going back and forth. Little gravitons going back and forth between other strings account for the gravitational force and also electromagnetic forces.
So Newton's theory that every particle in the universe attracts every other particle, no matter how far away, does this mean they have to be close enough so gravitons can pass between them?
Yes, it does mean exactly that. On the other hand, there's no limit to how far a graviton can travel. There's also no limit to how far things can be and still feel some degree of gravitation.
Is a graviton limited by the speed of light?
It is. Yes, a graviton is limited by the speed of light. And in fact, what that means in practice is if you have two objects which are attracting each other gravitationally, for example, strings going back and forth, and you suddenly come and give this one a pull, it doesn't affect the other one until light could have gotten across to them. It doesn't affect the other one until that graviton has a chance to get over to the other side. So, yes, it does take time for gravitation to travel.
Now, can this information be useful? With this understanding of gravity, could we maybe reverse gravity?
We know no way to reverse gravity, unfortunately.
Or cancel it out. That would help a lot.
As I get older and older, I wish more and more I could figure out a way to reverse gravity, but no. Gravity is universal. It's as universal as Newton thought that it was.
Now, we actually have some pictures of strings. Can we see that image, please? It's actually a computer rendition of a string. Can we see that graphic, please?
Oh, there it is. Okay. I
So
recognize it. I think I made it.
Yes.
Okay, what those are actually, those are very complicated strings. They're strings which have undergone a process, in fact, of falling toward a black hole. The one way over on the left is a string after it's gotten close to a black hole. As it gets closer and closer to the black hole, it begins to stretch and begin to make itself more and more complicated. And so the one on the far right is just before the string lands on the horizon of the black hole.
And disappears altogether forever?
What happens is it gets mixed up with a bunch of string on the horizon of the black hole. What's not shown in that picture is a sort of background of string that represents the horizon of the black hole. So what happens is it falls into this mess of string on the horizon and gets mixed up with it so thoroughly that it loses memory of which piece of the string was the one falling in and which one was the thing that made up the black hole. But I've separated them so that you could see them.
So it's like different levels of excitation of the string?
Exactly, different levels of excitation. As the string falls toward the horizon, it gets more and more excited, more and more stretched, more and more curly, more and more like a complex ball of wool, you know, that your cat has played with.
Now, I hear that strings exist in 10 dimensions at once. What do we mean by dimensions in this case? We usually think of the 3 spatial dimensions.
And time as a 4th dimension.
Although it's very different from the other 3.
It's a very different one. You measure it with a watch instead of a ruler. But when we say the number of dimensions, we're always including time as one of them. So there are 3 space directions, 1 time direction. Okay, of the 10 dimensions you're talking about, one of them is time, and the other is like having 9 perpendicular axes instead of just 3.
So they're all spatial dimensions.
They're all but one.
Okay. So does that imply that what we think of as our three-dimensional space has the capability or the potential to actually be a nine-dimensional space.
Yes, it does. Yes, it does. But why don't we see those 9 dimensions? In other words, why can't I move around in them and stuff? It's because they're very, very small. At least everything I'm saying, of course, is subject to the disclaimer that this is true if string theory is the correct theory of the world. I don't think we know that with utter certainty. So from now on, I won't say if string theory is the right theory. You can assume that I mean that.
Is there any way to test it?
String theory?
Yeah.
A lot of it, much of it is already tested in many ways. As I said, the most important and most central prediction of string theory, which no other theory really predicts, is the existence of gravity. So when I drop something, in some sense, I'm testing string theory. Now, most people would say, oh, come on, you're not really testing string theory, you're just testing gravity. And I sort of agree with that.
Well, we know that gravity exists. The question is the string theory the explanation of it?
That's right. That's right. So what I would say right now is it's the only theory that we have that gives an explanation. Does that mean it's the only theory that will ever be that gives an explanation? It does not mean that. But right now, it's the only theory that we have that implies the existence of gravity. And that, to me, is a serious business.
Now, string theory under development, there are new things happening. Is the theory being filled out, or has it reached a point where it's stopped developing?
No, it has not. It's been around 40 years almost 40 years. It keeps giving new insights into all kinds of things, cosmology, particle physics, gravitation, and to ignore it, to say, well, you haven't proved it, therefore you shouldn't be thinking about it, or there's no way to prove it, therefore you shouldn't be thinking about it, that strikes me as silly. We have this mathematical theory which does a number of things. It has particles in it, it has photons in it, it has electromagnetic forces, it has gravitation, but because all of these particles are so tiny and so remote from our senses that we don't have a good way to directly test it. Does that mean we shouldn't be thinking about it because it's too hard to confirm? Well, you could take that view.
Well, every theory is ridiculed before it's finally accepted as being valid.
Indeed.
So the question is, does string theory seem to have enough potential that physicists are willing to devote their careers to working on it?
Well, I think the best answer to that is that young physicists coming into the field flock to string theory. Of course, it's not the only thing that's interesting. There's lots of areas of physics which are very exciting, quantum computing, all sorts of things. But in some sense, a certain class of people with a certain bent of mind who are always the ones who were most curious about the fundamental laws of physics, those young people still flock, not just still, maybe more than ever, are coming into the field and finding all sorts of new and exciting discoveries.
And also the people who fund the research have to decide that it's worthwhile, so they must be finding it so.
Yes, well, they fund it. Don't ask me. I don't fund it myself.
So how can we really visualize the basic facts of existence? Is there some way of looking at it that gives an intuitive glance of what's really happening at that subatomic level?
Strings are banging against other strings, colliding, being exchanged with other strings, and in the process creating forces which bind things together, from nuclei to atoms to galaxies.
So could one string express itself as one proton if all of its attributes were set correctly? One string would be one proton.
That's where string theory began, as a theory of the proton. That's where it began in the first place, yes. So the answer is yes. A proton is a stringy-like thing. Now, protons we do experiments with. and we can collide protons with other things, and we do see that they behave like strings. So it's not completely right to say that string theory has never been confirmed. The places where it's not been confirmed or directly confirmed is basically when it comes to gravitational, to the tiny, tiny, tiny elements of gravity, which means the gravitons, which are vastly, vastly smaller than protons. And there it is proved very, very difficult to
Now, would a graviton
confirm.
be one string that's configured a certain way?
Yes, it would be one string that's configured in a particular special way. It is much, much smaller, many, many orders of magnitude smaller than the strings that make up protons. And the result is it's simply very, very much harder to get direct confirmation.
Now, when a physicist does research in string theory, what does he do? And does he work figuring
You mean what do I do all day
formulas?
long?
Yeah, is it working out mathematical formulas, or what do you do?
Well, let's see. I get into work around 10 o'clock. I find my colleagues, and we sit down and have coffee. After coffee, the coffee lasts for about an hour. All of that time, we are debating, discussing our latest thoughts, the thoughts we might have had the night before, and we are plotting, largely in our own heads, what we're going to spend the next 7 hours doing. And then we tend to go into our offices. Some of us stay at the blackboard, and sometimes I go in my office. I work out equations. I think about how these things are supposed to work. And then later in the day, I'll get together with my colleagues again, my students, my postdocs, other faculty, and we'll talk more about.
So when the people who are providing the funding say, what did you do in the past year?
We schmoozed.
All right, well.
You know the word.
Yes, of course.
Yes.
So that's how scientific progress takes place.
Yes. I don't know about all areas of science. I know about my own area of science, and it is a very social enterprise in a sense. People exchanging ideas left and right. It's almost a wild west of ideas being thrown back and forth. Some fraction of them stick. Some fraction of them stick, and then you work out the consequences of it. That can be extremely intense. That's when the intense part of it happens.
So is the main thing visualizing how things work and then attempting to explain it in the language of mathematics?
Yes. For me it is. Some of my colleagues tend to, I think visually. I do think visually. I close my eyes and try to see the phenomena. Some of my colleagues think in a different way. They think more algebraically. They tend to rely more on algebraic symbols and equations and so forth. So there's a variety of different types, let's call it. That's what makes the theory, that's what makes the whole thing work, that there are different people coming at it from different directions. But yes, for me, it's a process of visualization and then trying to convert that to mathematical formulas. And that's largely what I spend the day doing.
Now, let's say that string theory turned out to be true. What would we get from that? So early atomic theory resulted in the atomic bomb, for example. Where might string theory lead us?
It's very hard to say, but I think one of the places we hope that it will lead us to is a better theory of the creation of the universe, a better theory of how the universe began and why its properties are what they are, why the universe is expanding the way it is. We also want to know why the particular particles that we see, why the electron is so much lighter, for example, than the proton. The electron is about 2,000 times lighter than the proton. Why? Where did that come from? The hope is, and it has not been established, but the hope is that the equations of string theory will have answers to these questions, and we'll understand where we came from, at least insofar as the Big Bang and those things. Now, this is a dream. This is a dream. It's not a reality at the moment.
Well, all realities start out as dreams, right?
Yeah.
Now, I've heard the word multiverses or multi-universes in relation to string theory.
Yeah.
So what does that mean? There's more than one universe?
It's a matter of linguistics that there can only be one universe. Uni means one.
By definition?
By definition. But the universe we know, now this is a matter of empirical evidence. We know from astronomy, from cosmology, from, I'm talking about now observational cosmology, we know the universe is very much bigger than the portion we can see. The portion we can see is a tiny, tiny, tiny fragment of the whole thing. Now, string theory permits many, many different kinds of environments, many, many different kinds of spaces, times, particle, content, and so forth. And there's no reason to believe that the little piece that we see is characteristic of the whole thing. In this much, much bigger, let's call it a multiverse, there may be places over here where one set of solutions of string theory, which means some collection of particles, some collection of forces might hold sway. Some other place things may be different. It could well be that somewheres out there, there's a place where the electron is 2,000 times more massive than the proton.
So the model of the protons being in the nucleus and the electrons, according to string theory, it doesn't have to be that way.
It does not. We know that the equations of string theory have many, many different solutions. That means that they have many, many different kinds of possibilities that they can describe.
Being strings can express themselves in many different ways.
That's right. The strings can express themselves in many, many different kinds of ways. And that's what makes it so hard, incidentally, that there are so many possibilities. More possibilities probably than the possibilities for living organisms. And so we're stuck with a theory which is so rich that we have trouble finding our way through it and finding the particular version of it that describes our world. The string multiverse is sort of the collection of all of these worlds, all of the various possibility things that can happen and may actually happen in different places.
Now, do not see these other worlds because they're just too far away, or?
Yeah, they're too far away. That's a simple way. That's probably a slight oversimplification, but without equations and without blackboards, I think it's close enough that they're too far away.
Now, another area you've also done a lot of work in is black holes.
I have.
Which I have a vague understanding that it's a collapsed star that exerts so much gravitation that nothing can leave it.
Yeah.
So one question about black holes is, once a black hole is there, does it last forever as a permanent hazard to space navigation, or does it eventually disappear?
On very, very long time scales, many, many, many times the age of the universe, black holes will evaporate. Just like a puddle of water, you may watch it for an hour and you say that puddle isn't going anywhere, but if you watch it for 6 hours, you might discover that it evaporates.
Well, if it evaporates, doesn't that mean that some of its particles are leaving?
Yeah. Some of its particles are sort of boiling off the horizon. Boiling off the horizon is, I think, a good picture. And the time scale for this is very long. But at the present time now, most black holes are not evaporating and shrinking, they're growing. And the reason they're growing is because there are so many particles out there, photons and other kinds of particles, that it keeps absorbing them. A black hole that's out there has much more likelihood of catching something and absorbing it than it does of giving off its mass. So today, black holes are growing. In time, the universe will expand. As it expands, it will cool, it will become more and more empty, and sooner or later the black holes will start to evaporate. There won't be anything out there for them to absorb anymore, and they will start to evaporate. And then in some length of time, which is so long that it's inconceivable time scales, the black holes will themselves evaporate.
Do we know that the universe keeps expanding? And if it does, what is it expanding into? Is it in a larger medium that it expands into?
That's the wrong way to think about it. It's not expanding into something like that. It is all there is, and it's expanding. So the picture that people often imagine that describe things is a balloon being blown up. Well, you say, well, the balloon is being blown up, and it's being blown up into the rest of the room. It's a two-dimensional thing expanding into 3 dimensions. But don't think that way. Think that all there is the surface of the balloon. That's all there is. It has nothing to expand into. It itself just grows.
But the material is getting thinner on the surface.
Okay, that's rubber for you. Rubber, that's where rubber fails to be a good model of the universe. The universe, it's as if the rubber kept replenishing itself as it expanded.
So more space is being created?
More space, which is almost analogous to saying that as the rubber balloon expands, more and more rubber comes to fill in the holes between the, that's left by the expansion.
Will most stars become black holes eventually?
Well, that's a different question. I don't know what the ratio is of stars that will and won't. If the star is like our sun, it's not heavy enough to form a black hole. It'll form, I think, a white dwarf. A white dwarf is a thing which isn't heavy enough to collapse under its own weight and form a black hole. A star which was, let's say, 10 times heavier, and there are plenty of such stars out there, they will collapse under their own weight and form black holes. So some fraction of them will form black holes, some fraction of them will form neutron stars, pulsars, some fraction of them will form these white dwarfs.
We just have about a minute left, so could you wrap your explanation of the theory up in 30 seconds or so, leave us with something optimistic?
Well, I'm very optimistic, but I'm always optimistic. Look, I think the best thing to say now is it's a work in progress. It is the best idea that we have out there for explaining the basic laws of physics. In fact, I would almost say it's the only good idea out there, but that in itself doesn't mean it's right.
Okay, and we're going to have to leave it at that because I've gotten the signal. I'd like to thank my guest, Leonard Susskind, physics professor at Stanford. Thanks for being here.
You're welcome.
Thank you for watching. Visit our website, www.futuretalk.net. For Future Talk, I'm Marty Wasserman, and we'll see you next time.